Hello everyone. So today we will talk about exercise 8.29, moving plane. So this question is about this ball of mass m on a slope with mass capital M. And this slope lies on a frictionless plane. And there's a ball of mass of small m on there. And the slope angle is theta. And so this m rolls down the slope without slipping, causing an horizontal acceleration of the plane. And the question is asking us to find this horizontal acceleration. So what could it be? Well, this question gives us a hint. It tells us that we should try to use the conservation of energy here. So let's just go back to the basics and just list out the conservation of energy equation. So for this problem, I'm going to use this notation. So capital V, big V, represents the velocity of the slope, and small v is the velocity of the ball. And so now let's try to do that. Let's consider the case when the ball of mass has already rolled off the slope, when it's going away. Then what is the formula? Let's say the initial height of this ball of mass is h. Then we have initial energy is mgh equals to half big M big V squared plus small m v small v squared plus the rotational kinetic energy. So this is when the ball is already here, it's moving off already. And so that's the case we're listing the equation, because otherwise we would have to include another term, and that would just make the problem unnecessarily complicated. So let's see what else do we know. Let's try to eliminate some variables here, right? So we have big V, we have small v. So what can we do? Let's consider momentum here. Momentum is not conserved here. The vertical momentum is not conserved because there's gravity. So gravity is an external force. But in the horizontal direction, P of x, the total net horizontal momentum is conserved. Why? Well, because if you look at the forces here, what do we see? We see normal force, we see friction, we see gravity, right? So the only forces that have horizontal components are friction and normal force. And these two forces are all internal forces. So that is why the momentum in the horizontal direction is conserved. So then based on this, we can list out. Originally we said the ball starts at rest, right? The question also says that it's released. That means it's at rest. So the total momentum should always be zero. And that is equals to big M, big V plus small m, small v. So here then we know that uh, small v, so we know this. And then so we know big M V equals to small m v negative. And so then we know that small v is m over negative m big V. And so here we've eliminated some variables here. And keep in mind that this V here is in the horizontal direction, right? Because Vy has something to do with the momentum in the y direction, and that is not something we're considering right now. We can only say that for V of x, the horizontal velocity of the sphere, of this ball of mass, equals to big M over negative small m times big V. And so how is that useful? Let's try to think a bit more. We know that v squared equals to vx squared plus vy squared. We already have vx squared. So now, what can we do with vy? So what are some of the conditions that we haven't used? So if we look at this diagram, what do we know? Well, we know that this sphere, this ball of mass, must move along the slope, and that slope is angle theta. And so that theta should never change and should sort of constrain the motion of this ball of mass. So let's try to think. Remember how we said the height of this ball of mass, we call that h, small h. And then now we just need this, right? We know that tangent theta is opposite or adjacent, so h over whatever this is should be constant. So what might this be? So if we think about it, let me just duplicate this diagram first. If, let's say, the slope moved a bit, right? And then let's say the sphere moved to here. What can we say? Well, let's look at how both of these objects' positions changed. So if we look at here, the sphere moved some distance. Let's call that d, small d. And then the big mass, the slope, also moved a distance, big D, let's call it. And so then the total distance of separation increased is big D plus small d. And then the displacement, the changing height of this sphere, of this ball of mass, let's call it just h. Then do we agree that tangent theta is h over d plus d? Or to put it more clearly, do we first agree, let's say if this is the vertical, this is the, sorry, let's say if this is the horizontal velocity of the ball of mass and this is the vertical, do we agree that tangent theta equals to Vy over Vx? So that is a constraint. The sphere, the ball of mass, must follow. So if we agree with that, then we know that it should just be equals to delta y over delta x. The change in the y direction over the change in the x direction is tangent theta, and that should not change. Otherwise, the ball of mass would fly off the slope. And so then we said that delta y is h and delta x is big D plus small d. And now let's try to eliminate some variables again. So remember how we said that Vx equals to m over negative m times big V. So let's try to figure out some way to relate small d and big D. And how can we do that? Well, if we integrate each side with respect to time, right, we will have d equals to m over m big D. And take note that the negative sign disappeared because we defined d and d to be the displacement, the distance. So these d and d on themselves are positive. We define them to be a positive distance. Remember that distance is a scalar and there's no positive or negative. It's always positive. And so then the displacement of the slope technically should be negative d. That's the displacement of the slope of m. And the displacement of small m is just d. And that's why we said that, d minus negative d is just d plus d. And that's why it's d plus d here. I didn't write that because it's quite intuitive from the diagram to just see, oh, this is d, that's distance, and this is big D and the distance. And adding them together gives the change in the x direction. And so then here, technically, when we did that, we will have d equals to negative m over m. This would be negative d to signify the displacement. Because remember, this is velocity and we're integrating it by time. So the integral of velocity with respect to time is the displacement. And so we must write it in displacement notation. And that's why we have a negative sign here. And after cancelling the negative sign, we have d equals to big M over small m, big D. And so then remember the relation we said that tangent theta is h over big D plus small d. And so then we can rewrite that as h over d1 plus big M over small m is equals to tangent theta. And then next, what can we do? Well, let's just try to look back at the equation that we wrote. we wrote this, we have this relation, and we have the d relation, and that's also tangent theta. So let's try to plug it in and see what we get. So I'm just going to rewrite it here. mgh equals to half big mv squared plus half small mv squared. Let's write it as vx squared plus vy squared plus, what do we have? We have the rotation, so half I omega squared. And we had the relation of tangent theta equals to h over d 1 plus m over m. We also had v equals to negative m over m of big V. And so now we have these three relations, and let's try to plug it in some way. So first look at the left side. So from this equation we get that h equals to tangent theta and then big D 1 plus m over m. So we have mg d tangent theta 1 plus m over m equals to half mv squared. So there's nothing to be done here. And then next, sorry, I meant vx equals to negative big M over small m equals to big V, because that's the horizontal momentum conservation, plus half m, that would just be m over m squared big V squared plus Vy squared. So this one we haven't figured out yet, but I'll tell you next what we should do. Plus half I omega squared. Remember that I is beta mr squared in this case. So we have half beta mr squared of V squared over R squared. So again, V squared over R squared. And then next, what can we do? Well, let's think about Vy. What can we say about Vy? So previously we said h is the vertical position of the ball of mass. So then we can relate Vy and h through this relation, right? And then we knew that h is tangent theta d 1 plus m over small m. And so then dh over dt is, look, this is constant, and that is also constant. So what's left is only this d here. So this is a bad notation, but just, what is the derivative of the distance with respect to time? That's just velocity, right? So that's just the velocity of the slope. And so we have v tangent theta of 1 plus m over m is equals to Vy. So that is Vy, the expression. And so now if we plug it in, I'm just going to copy this so it's clear. So I copy that and then paste it here. We will get mgd tangent theta 1 plus big M over small m equals to half mv squared plus half small m big M over small m squared v squared plus, what's Vy squared? Vy squared would just be tangent squared theta 1 plus big M over small m squared v squared plus half beta m r squared over v squared over r squared. So this v, we might be tempted to just write v squared is vx squared plus vy squared and plug in as is, but this is wrong, because this v should be the relative velocity rather than just the velocity of the ball on its own. And so then what can we do? So just remember that here in the system, both the slope and the ball are just moving, right? And so that v is really not the v of the ball of mass itself when we are calculating the rotation of this sphere. The rotation has to satisfy, so this v, so we know that omega, right? Omega has to be v over r, and that v is the net velocity, right? The ball is moving that way, the slope is moving that way, and the omega has to compensate for that. The omega has to be larger than what would just be v over r, what would just be v ball over r. it will have to be both. It will have to account for both the slope and the sphere itself in order for this sphere to rotate without slipping. And so then what can we do? Well, we know that the relative velocity along the x direction is just big V plus small v. And previously we said that big V, big M over small m times big V is just small v. And so then here we have 1 plus m over m. Big V is the relative velocity along the x direction. And so next, what can we do? We know that the v relative direction times cosine theta is v relative direction along the x direction. So then v, the relative velocity, it's just 1 plus m over m, big V over cosine theta. And so next, the actual equation for the setup should just be small mg d tangent theta 1 plus big M over small m equals to half big M big V squared plus half m big M over small m squared V squared plus tangent squared theta 1 plus big M over small m squared V squared plus half beta m r squared 1 plus big M over small m squared V squared cosine squared theta. And then there's an r squared, so we cancel out the r squared. And so next, what can we do? Well, let's try to eliminate one of these variables. So how can we do that? Well, we know that v and d are definitely related, right? Because they're all about the slope. So let's think. Let's think about acceleration here. If we look at the system, what do we know? Well, we see that almost everything is constant in the system, right? The mass, the angle, the friction, the normal force, the gravity, these are all constant. And so the acceleration of the slope must also be constant. So if that makes sense, let's just say let A be the acceleration of the slope. Then we know that A is constant because all other parameters, all other forces are always constant. So then A must be constant all the time too. And so then we can think back to the kinematics equations that we studied at the start of learning physics. We just know that v squared minus v naught squared equals to 2a d. D is the displacement. And we know that v0 is 0 in this case because the system starts at rest. So big V squared is 2ad. And so we can get acceleration through this formula, v squared over 2d. And that is possible because if we isolate out v squared in this equation, we have a d on the top of that fraction. And so then that will cancel out and we'll get an acceleration with no variable whatsoever. And so now how can we simplify this? Let me first just try to copy paste this equation so I don't have to rewrite it later on. So copy and then paste it here. And then I'm just gonna erase some of these scratches. And so now what can we do to isolate v squared? So now our task is to isolate v squared. So first let's factor out half v squared on the right. So mgd tangent theta 1 plus big M over small m equals to half v squared big M plus this term we have half m big M over small m squared v squared. Oh, I'm sorry about this. This should be squared. So this term should be squared here. And so then we will have v squared is non-existent here. So it's just half m times big M over small m squared. Half is not here either. And then next we have plus m. So if we look at this term, we have m tangent squared theta, and then 1 plus big M over small m squared. Let me just write it more neatly. Right? And then this term will have plus beta m, 1 plus big M over small m squared over cosine squared theta. Next, we can simplify this a bit more. We have on the left side, it doesn't change much. And then on the right side, we have half v squared plus m squared over small m plus m tangent squared theta, 1 plus big M over small m squared plus beta m 1 plus big M over small m squared over cosine squared theta. And next, what can we do? We have mgd tangent theta 1 plus big M over small m equals to half v squared. So what can we do with this term? Well, we can factor out a big M, but since we have small m's here, let's try to factor out something with a small m, so then we can actually cancel out the small m later. So we have, this just simplifies to m over big M over small m times 1 plus big M over small m plus m tangent squared theta 1 plus big M over small m squared plus beta m 1 plus big M over small m squared over cosine squared theta. And so then we have mgd tangent theta 1 plus big M over small m. Actually, we can just cancel now. So if we look at this, what can we do? We can cancel out small m and 1 plus m over m. So this goes away, this goes away, this goes away, this goes away. So it's this, and the square goes away, and then m and this. So what we get eventually is g d tangent theta 1 plus big M over small m equals to half big V squared, big M over small m plus tangent squared theta 1 plus big M over small m plus beta 1 plus big M over small m cosine squared theta. And so next, what can we do? Now let's just isolate V squared because there isn't really much to simplify. So 2gd tangent theta 1 plus big M over small m over, so we move that down, we have big M over small m plus 1 plus big M over small m. So if we factor out the 1 plus big M over small m, we have tangent theta squared plus beta over cosine squared theta. So we can write it in a fancy notation, secant equals to v squared. And so then previously we said that v squared minus v0 squared is 2ad. So a equals to v squared over 2d because this was 0, the system was at rest initially. So then we have just this thing over 2d, which is g tangent theta 1 plus m over m plus m over m plus 1 plus m over m tangent squared theta plus beta secant squared theta. And that is our answer to exercise 8.29. Thank you for watching.